Hi again, guys. Today, what I want to go over with you is resistance. So resistance is essentially what circuits do to current. Current tries to move through a circuit, and there are items within a circuit which will resist the current, which will put up some resistance towards that flow of charge. So I have a template, a blank set of notes that I posted on the module. So you guys might go ahead and print those out before you watch this video. And then I'm going to go through the notes that are on that blank template. So think of that as like an organizer that kind of help you write down the important stuff as we deal with resistance. So I'm going to go ahead and switch over to my overhead, and you'll see a copy of the notes. You guys might want to pause it right now and print out your blank copy so that you guys can kind of follow along with me. Okay, as we start to talk about resistance, what I want to first mention is I want to review what we've talked about already about potential difference and current. Remember that a potential difference is what you're going to get if we talk about a simple direct current is what this would be. The current only flows in one direction. If we talk about a simple battery setup, what you see here would be a circuit. There's a path that goes from the negative side of the battery all the way to the positive side of the battery, which would allow those electrons that are collecting on the negative side of the battery. Remember, they're repelling each other. You have a deficit. You don't have as many electrons on the positive side. And so the positive side is pulling the negative electrons towards it. And the negative side is pushing those negative electrons. They don't like being close to each other. And so they're repelling each other and pushing them in this direction. Now, that said, don't forget that the traditional idea of current is not movement from negative to positive. The traditional idea of current is actually in the opposite direction, from positive to negative, because they didn't realize it was the electrons that were actually moving. They didn't even know that electrons existed. So they had to pick one or the other to move, and they chose positive. Unfortunately, it's a 50-50, and they picked wrong. All right, so don't forget, though, that it is a potential difference. All right, we need a potential difference. Provides the push that causes current to flow. Okay, so it is the potential difference that you would have in this battery. Let's say this battery, typically a 9-volt, a 9-volt would be 9 volts, but typically like an A, a double A, a C cell, a D cell. Let's just say that's a D cell. It doesn't really matter. They're all the same. They all provide a push of 1.5 volts. Remember, it is the unit for potential difference is volts. And that's the difference that you get between these that forces those electrons to move. Okay? Without a potential difference, we talked about this in the last section, without this potential difference, you won't get a push and you won't get current. Fact is, that's kind of what happens. Let's say you got a flashlight that you accidentally left on. Well, the whole time that it's running, you'd have a light bulb, obviously, in this circuit. But these electrons would be moving. The whole time it's on, these electrons are moving. Now, if you think about that, eventually what will happen is so many electrons will move, the difference between these two starts to get smaller and smaller and smaller because you're piling up electrons here and taking them from here. And eventually you get to the point where you pile up so many electrons at the positive side that it no longer pulls these guys. You don't have that potential difference. And you would say your battery is dead. Okay, so you'd either have to recharge it if it's rechargeable or put new batteries in. So that battery gives you the potential difference, and that's what forces the current to move. The problem that I have with this very, very, very simple circuit that I've drawn here with a line, a conductor that goes from negative to positive, or again, if we're talking about the old way of thinking about current, from positive to negative, so they would say it would be positive charges moving this way. There's nothing in here to slow down these electrons. There's nothing to slow them down. And so they will just very quickly run from one side to the other. They can run so quickly that this wire would heat up and maybe even melt the plastic that's around it. Or if it's in close contact, if this was in your walls, for instance, it could cause a fire. So what we have here, when we have no resistance, nothing really slowing this down, we would call this a short, meant to do this in red. This is a short circuit. You may have heard of a short circuit before. A short circuit is simply when you have a path that goes from one side of your potential difference, the negative, let's say, to the positive, with nothing really in between to slow it down, like a motor or a light bulb, any electrical device that would put up more resistance. And so this would make your batteries go dead very quickly, is what it would do with the short circuit. And it can be dangerous because it can start fires. So basically the problem that we have with this circuit, you guys, is this circuit does nothing for us. The whole reason we want things with batteries, our cell phones and our iPods or whatever we happen to have, our laptops, all this kind of stuff that we want that current as it moves, we want those little electrons to do work for us. And this one does really no work. So what we have to do is we have to put something in that circuit that actually helps us. Otherwise, this is just kind of a trick, is all it is, that doesn't do any good for us. Okay? So what we need to have then is we need to put in some type of resistive element. Some resistive element is a fancy way of saying we need to put something in there that those electrons can do work on. Okay, we want them to do work as they move from one side to the other. So we set it up, and I'm just going to say let's put a simple fan in here. So if we did this, we would get our electrons and they would move. But when they came and went through the motor here, they would do some work, okay, as they move towards that positive side. Once again, I am drawing this current in the direction that the electrons move, but remember the actual current is in the opposite direction, from positive to negative. So if we think about this fan, what this fan is doing is it is using some of the current. It's going to use some of the current to convert, if you think about it, it's converting electrical potential could really say, I guess, electrical potential difference to, well, think about what this fan's doing. This converted that the electrical energy, it's being converted into kinetic energy, the motion of the fan blades. See, that is basically an example of electricity being used to do work. It converts one type of energy into a different type of energy. And really, I guess you could say it'd be rotational. This is spinning. So you're getting rotational energy out of this, which drives the fan blade. So we're making that conversion. It's doing something for us. Okay. This is what we want to use current to do, electricity to do. And we have to put these elements in here, like this motor. This is going to be the device that does that work. But in exchange, you don't get any kind of energy for free. You can't just get kinetic energy from nowhere. That would violate the conservation of energy rule. So that energy had to come from somewhere, and where it came from was the energy that these moving electrons had. They had energy which was then converted into kinetic, and that means that we can still kind of balance the energy involved here. It just changes to a different type. It doesn't get created out of nothing. Okay? So basically, every item, you guys, that we use to get work from a flowing charge, from current, is going to provide some resistance to that current. It'll slow it down. Even the wires that we use to conduct electricity from one place to another, even these wires will present some resistance. And if we use the kind of the water analogy that I talked about before, think of this flow of electrons being like a stream that flows from high elevation to lower elevation. Well, as it flows, it's going to bump into things. If this was a stream with water in it, that water's going to bump into rocks. It's going to rub on the bottom of the stream. It's going to run into things, and that's going to slow it down. Well, so the same thing goes for these moving charges. They bump into the atoms that make up the wire. The wire's made from copper. And that copper is going to provide some resistance, just like the bottom of a stream or the rocks that might be in the stream. The water bumps into those, it slows them down. The electrons bump into the copper atoms, and that slows them down. Okay? They both provide resistance. So we have a basic definition of resistance that I want you guys to know. I want to make sure I get exactly the right one, because I'll tend to define this in a little less scientific way. I would basically say resistance is the I want to use the word resistance in the definition of resistance. It's the slowing down of charge in a conductor. So what they actually say, this is in the book, they say this is the opposition to the flow of current in a conductor. Oops. Now, you guys at this point, I hope, recognize that a conductor is simply a substance that will allow electricity to flow through it. That's what a conductor is. All right, the opposite of a conductor is an insulator, and that's an object that doesn't allow electricity to flow through it. So, for instance, most metals, almost anything you can find that is made from metal, is going to be a conductor. Most objects that are non-metals, like plastic, like wood, these kinds of things, are either really, really, really poor conductors, or we would basically say they don't conduct at all. They are insulators. Okay. We measure resistance. Okay, we measure resistance in units that are called ohms. Okay, so ohms is the unit that we use to measure resistance, and the symbol that represents ohms is the Greek symbol. I guess it'd be a letter, omega. And it looks like this. You guys may have seen this before and not realized it. That's the symbol for omega. So if you see this, this is showing you, if you look on an electronic device, this will show you how much resistance that device is going to put up to current flowing through it. And what we usually say with most objects is that most objects have a constant resistance. It's not going to vary no matter how much current you try to shove through it. It's going to provide the same resistance. We call those objects ohmic. So there are some objects which do vary. Their resistance varies depending upon how much current you try to push through it or what direction the current is going in. So for instance, you may have heard of an electric device called a diode. Diodes allow current to flow one direction, but if you try to push current through in the other direction, it's like a roadblock. It doesn't let it go through. And so a diode would be an object that is non-ohmic. It doesn't allow the same current to flow through no matter what. All right. So many objects are ohmic, and there are some that are non-ohmic though, where the amount of current you try to push or the direction that you try to push, it provides a different amount of resistance. Okay. So that's this side. We basically talked about what resistance is, the fact that we need to put objects in that provide resistance in order to get work. Excuse me. And the fact that pretty much any object that we put in an electric circuit, go back to that circuit, any object that we put in this circuit will provide some resistance. Not every object provides the same resistance. So for instance, wire provides relatively low resistance, but that motor is going to provide a lot more. Okay, so they're going to differ just a little bit depending on what the object is. And we saw a definition of resistance that it's measured in ohms and represented by the symbol omega. Okay, so we are going to go to the second page here, talk a little bit more about resistance. Something that you guys should know is that there is a relationship between potential difference, resistance, and current. And this should kind of make some sense to you, I hope. We'll talk a little bit about that once I tell you that this relationship, this mathematical relationship, is something that's called Ohm's law. And basically, Ohm's law looks like this. V equals I R. Okay? Where V is voltage. Okay? Let me write that with a different color. Okay, this is voltage. Or we also know this as potential difference. Okay, so V is voltage or potential difference. I is current. This shouldn't be anything new to you guys. We've been over this before. Okay, so I is current. And R, this is the new one. This is resistance. Okay, R is resistance. So if you think about this, I hope this will make sense to you guys. And that is, this is V, this is my potential difference, and this is my resistance for the light bulb. V is going to give me my push. That's what's pushing that current through this circuit. But the higher my value of R is, the more the resistance is. Think about a stream, for instance. If this was a stream where I have a certain flow of water through the stream, well, what if I took that stream and instead of having it be concrete line like a canal, like a concrete, nice, smooth line canal, that doesn't provide a lot of resistance. So what about the amount of current you could push through that? Well, you'd be able to push a lot of current through that canal if it didn't put up much resistance to that current. However, if I took a bunch of rocks and I threw them in and I lined the whole bottom of that canal, then now it starts to provide more resistance. And so the way this works with electricity is the more resistance you get, the less current you're going to be able to have. Remember, the definition of resistance was just the resistance to flow of current. So the more resistance you have, the less current you get. Now, what if I put more force on it? What if my push was bigger? My potential difference, instead of 1.5 volts, it was 3 volts. Well, if I were to double the potential difference, the push is greater, I'm going to be able to move more current at the same resistance, okay? If I push harder, I'm going to move more water. This would be equivalent, if you talk about a stream, to taking a stream where the difference in height between here and here was maybe 2 feet, and then I have another stream that's exactly the same, but now the difference in height between here and here is 4 feet. I'm obviously going to get more flow if it's steeper. Well, this is kind of like steepness right here. If I have 3 volts instead of 1.5, I'm going to get more flow if I keep the resistance the same. Okay. So if I were to look at this as a for instance, I can solve for this. The one variable that I don't have in this circuit right here, I've got V and I've got R, I'm missing I. So if I wanted to know what the current is here, this wouldn't be too hard to do. I would take my formula that I got, V equals IR. If I'm solving for I, okay, if I'm solving for I would divide both sides by R to isolate I. Okay, so that would cancel those, and I would get I, the current, equals V over R, or in our case over here, 1.5 over the resistance, which is 1 ohm. And if I do that, I'm going to get my current, which would be 1.5 amps. Okay. So it's pretty easy to use this formula to figure out current. If you know 2 of these, you can figure out the other one pretty easily by just doing a little bit of algebra. Okay, and you guys are going to get an assignment that is similar to that tomorrow. All right, moving on. There are certain factors, if we think about a conductor, like a wire, there are certain factors that are going to influence resistance in a conductor. So, and if you kind of think of this in terms of the water analogy again, this should kind of make some sense to you. The first factor is that if you have a very long conductor, so if I've got 100 meters of wire that I'm trying to push electricity through, it's going to give me a different resistance than if I only have 10 meters. So if I go from 10 meters to 100 meters, there's going to be more resistance in the 100 meters. Okay, so the way that length works, the longer the conductor, the greater the resistance. So again, I hope that this makes sense to you guys. If I have a short wire, I don't have to worry about running into as many copper atoms to get to the other side. So for instance, if I had a 10-meter wire, I'm going to have a certain amount of resistance. If I have a 100-meter wire, I'm going to run into a lot more copper atoms if I go through 100 meters. And so that's going to mean I'm not going to be able to move that current as quickly. Okay, I won't be able to move charge as fast. And remember, the rate at which charge moves is current. So I'm going to get less current. So I'll say longer equals less current. Okay, that's the relationship. The longer the wire, the lower the current. Okay, the second factor that I want to go over with you guys is what is called cross-sectional area. And if you think about this, this is essentially if I have a wire, it's going to have a certain thickness. I mean, let's just say that my pen here is my wire. The thickness of this pen is going to determine the pathways that are available for current to move from one place to another. And so the wider that it is, the further across that is, the bigger that cross-sectional area is, okay, the more space that electrons have to move through. Okay, I'm going to be able to move more electrons through a thick wire than I am through a thin wire. So that means thicker wire, or I'll say larger cross-sectional area means more space for charges to move and greater current. So here I said longer equals less current. What I'll say here is thicker equals greater current. Okay, again, hopefully that makes sense in terms of the thickness of the wire. If you look, you guys, if you look at the wires they use to move electricity, like between cities. So for instance, if you're driving to San Diego, when you hit the desert, you hit this big, huge transmission line that goes across the highway out there, just not long after you go into the actual desert on Interstate 8. And the wires that are hanging on those towers are quite thick. I mean, they're probably 4 or 5 inches thick, each one of those wires is. As opposed to the wires that go to the devices inside of your house, they're probably half the size of a pencil diameter. They're really not that large at all because they don't need to move as much current. We want to move a lot of current in those transmission lines going to San Diego, so we want to make them nice and thick. Okay, we can't do anything about the length of that transmission line going to San Diego because there's a certain distance from Imperial Valley to San Diego. And so they have to be a certain length. We can't control that, but we can control how thick they are. So the thicker we make them, the more current we're going to be able to move. The third thing that influences resistance in conductors is what they're made out of. Okay, and what I would say is that some materials just provide less resistance. Okay, so for instance, copper, what we would say is that copper, let me write this in a different color, as an example, provides less resistance, I'll just use a less than say iron. Okay, copper is a conductor that provides less resistance than iron does. So that's why we make one of the reasons at least, that we make our wire from copper. Now, even better than copper, let me draw a little one here, is gold. Okay, we could make our that doesn't look like a less than sign now, but anyways, you guys are listening, so you know what I'm saying. Gold provides less resistance than copper, so why not use gold for our wires? Well, there's a price issue. So what you will find, though, is that we do use gold wires in applications where the lack of resistance is much more important than the money even. So for instance, on space satellites and things like that, and the probes that we send to Mars and the rovers and stuff like that, we'll use silver or we'll use gold for those wires because we lose less of our electricity because of the fact that on Mars, we can't just plug into something. We have to generate our own power on Mars, and any power that we lose is very, very, very costly. It keeps us from doing things. And so we want to reduce the resistance as much as possible. So we want to use, even though they're expensive, we'll use gold or we'll use silver instead of copper. So copper is kind of a trade-off. It gives pretty low resistance, but it also doesn't cost quite as much as other substances that may give even lower resistance, but they're just too expensive. Okay. And lastly, temperature. Temperature changes resistance. And so what we would say is, if you've got a short circuit, I mentioned that earlier, and it starts to heat up the wire, what ends up happening is, because the wire gets hot, it provides even more resistance. So it's kind of a runaway thing where a little bit of resistance starts to heat up the wire, and as the wire gets hot, it provides even more resistance, which heats up the wire even more. And it's what we call a positive feedback loop is what that's called. But the end result is it makes the wire so hot that the wire will start to glow and it can catch things on fire. So the relationship here is higher temperature, higher temp equals more resistance. So if we think about moving electricity, moving current from one place to another, we want to do the things that that reduce resistance as much as possible. We want to move as much electricity as quickly as we can. So again, if we think about that big power line that goes back and forth, well, mainly towards San Diego is the direction the electricity flows, but that moves electricity to San Diego, we can't control the length. The length is what the length is, but I would say this, we don't want to follow a path. If we're going to put a big long power line in that goes all the way to San Diego, we don't want to follow like a zigzag path that would increase the length that the wire has to travel. We want it to be as much a straight line as we possibly can. So they want to try to keep that power line going in as straight a line as possible to reduce the length, because the shorter we make it, the more current you're going to get. Okay. Cross-sectional area. We want thick wire. That thick wire is going to allow for more current to flow. Remember, the thicker it is, the greater the current you're going to get. We're going to want to choose a material that just has naturally low resistance. And so we're going to choose something like copper, for instance, that allows for a lot of current to flow. It doesn't provide a lot of resistance. And then lastly, we'd like to keep it as cool as we can, because the cooler that wire stays, the less resistance you're going to get. Okay, so these are all factors that influence the resistance that you're going to get in a conductor. And then finally, what I'm going to say on this is a practical use of things that offer resistance. We have these little devices called resistors, and we can use these in electronics to control current. So a good example of this would be like a ceiling fan. If we look at a ceiling fan, you'd have incoming current, and then you know how on your ceiling fan you have like a little chain and you can pull the chain and it changes the speed of the ceiling fan? Well, the way that motors work is they run at different speeds depending on the current that run through them. And so the more current you allow through the motor, the faster the motor runs. And so your fan speed's going to be high. So what they commonly do when you pull on that chain, what you're doing, each time you pull on it, it's turning a rotary switch. Rotary just means it turns, it spins. And that rotary switch, what it's going to do is it's going to have three possible directions that the current can flow through. Now, right now, the way that it's set, it's running through this resistor here. This is, we'll see this later, but this is a symbol for a resistor. And it's 10 ohms of resistance. If you turn this dial, if I turn this thing and I turn it back 1, the 5 would be in line there. So you'd have 5 ohms or 10 ohms or 15 ohms, and you control which of those resistors are going to be in line with this wire. So right now it has the middle amount of resistance. So you'd expect the middle speed on the fan. If the 5 was in line with this, if it had the lowest resistance, what would that mean about current? The lowest resistance means the greatest current. Remember, resistance is slowing down the flow of current. If I don't have much resistance, so the 5's in line here, I'm not going to get a lot of resistance. That means I'm going to get more current, which means I'm going to get a higher fan speed. On the other hand, if the 15's in line here, okay, I'm going to get more resistance to that flow of current. More resistance to the flow means less current. Less current means slower speed. Okay, so I'm saying right here, the more resistance you get, the less current you're going to get. And the less current you're going to get, the slower the speed's going to be. So which of these resistors is going to give you the fastest speed? Fastest speed is going to come from the greatest current. And I'm going to get the greatest current when I have the lowest resistance. It takes a little bit of logic here, you guys, but it's not really too hard to understand if you understand that resistance decreases current. So if I have the lowest resistance, I'm going to have the highest current. And that highest current is going to give me the fastest speed on my motor. Okay? So this is kind of a use that you would have for this whole concept of resistance, potential difference, which is providing the push, current, which is the movement of charge, and then the resistance is going to alter your current because it slows it down. That's what resistors do. Okay, you guys, I'm going to stop right there. There will be a quiz on this stuff, so make sure you guys take that thing after you've watched this video, and I hope you understand a little bit more about electricity and resistance. We will see you guys next time.